So hello, everyone, and welcome to Microsoft Research Reinforcement Learning Day 2021. My name is Akshay Krishnamurthy. I'm a researcher at MSR in New York City, and I'm excited to welcome you all to this year's event. This is our third iteration of MSR RL Day. The last two iterations, in fall 2018 and 2019, took place in person in New York City. Due to the coronavirus pandemic, we've moved to the virtual format this year, and there are two positive outcomes here. First, registration has increased by a factor of about 4 from 2019, with over 700 people registered today. Second, we have attendees and presenters from all over the world, and it's really great to see such enthusiasm for reinforcement learning. So my job here is to mostly just run through some logistics and housekeeping, and to make sure you all are familiar with the schedule and how to use the Teams app. The two main sources of information for today are the RL Day 2021 website and the Teams app. Both of these you can access via the tiny URLs displayed on my slide. You also should have received an email from msrrlday@microsoft.com with event details and links for accessing the talks and the posters. Before diving in, I just want to take a moment and give a shout out to my co-organizers, Ching An, Dipendra, Ida, and Robert. I also want to give a huge shout out to Brittany Muller and Jessica Mastronardi from MSR Outreach. This event simply would not have happened without the enormous amount of work that they did behind the scenes. Turning to the schedule, the day consists of two parts. The first part, which starts now, will include a keynote talk by Doina Precup and a debate between Yoshua Bengio and John Langford. Then we'll have a 30-minute break, and we'll reconvene at 12:15 p.m. Eastern Time for part 2, which is a poster session. We have assembled about 20 awesome posters, including some from MSR people and some from external contributions, for you all to check out. Since many of you may not be familiar with Teams or Teams Live, I just want to go over some of the important elements. Part 1, the talks, will be broadcast on Teams Live. If you can hear and see me and my slides, then you are in the right place. Teams Live restricts interactivity to a question and answer feature, but we do encourage you to use this feature during the talks. To access the Q&A tab, click on the icon in the top right of your Teams Live window. The icon is a couple of chat blurbs, where one has a question mark in it. And from here, you can type up a question and ask it. You can also view and vote on questions that others have asked. Questions, so your question may not immediately appear in your view. We'll publish some, answer some over text, and we'll also save some to ask the speakers. Teams Live. The tiny URL on the slide will open the app and take you to the right place. Each poster has its own Teams meeting, which is just a video call, like all the other ones that we're so familiar with these days. There are two ways to join these meetings. The first is by simply clicking on the links in the event access email that you received. The second is in the Teams app itself. Each poster has a dedicated channel in the app, and you can join the meeting by clicking on the channel and joining the meeting from there. There's also a chat thread associated with each poster's meeting and channel, and you should feel free to ask questions there over text. In the meeting, you can access this by clicking on the icon on the top right of your meeting window. You can also find the papers associated with each poster in the channel view by clicking on the Files tab. Finally, there's a general channel in the Teams app, which we've left open for any other discussions that may come up. This may all sound a bit confusing, but once you get into it, I think it will actually be pretty intuitive. If it's not, I want to point out that we have a code of conduct, so please let us know if you witness any problematic behavior. Finally, I wouldn't be doing my job if I didn't also announce that MSR is hiring in reinforcement learning and adjacent areas at all levels. If you're interested, please check out our openings at this URL, or get in touch with an MSR researcher during the event. And now that we have all the logistical stuff out of the way, I'll turn it over to Ida Momennejad, who will be introducing our first speaker. Ida?
Thank you, Akshay. Hello, everyone. I'm excited to be here. It is my absolute pleasure to introduce Dr. Doina Precup, who is an associate professor in the School of Computer Science at McGill University and co-directing the Reasoning and Learning Lab. She's a key and active member of the Montreal AI ecosystem, including Mila and DeepMind Montreal. She's a rare breed of computer scientists whose pioneering work in hierarchical reinforcement learning are not only relevant 2 decades after publication, but keep generating and inspiring new research in CS, neuroscience, and other disciplines. In my opinion, among her achievements are engaging in broad interdisciplinary discourse and mentoring impressive trainees. I'm excited to hear her talks and the following discussion. Please join me in welcoming Dr. Doina Precup and add your questions throughout the talk. You won't see the questions immediately because we're moderating it, but we're excited to hear them. Thank you.
Thank you very much for the kind introduction and for the opportunity to speak at this meeting. I'm really delighted to be here. I will tell you a little bit today about some new advances in hierarchical reinforcement learning that we have been making over the last couple of years, both at McGill University and Mila, as well as at DeepMind, which is my other dual affiliation. So what I want to talk about today is actually a very old way of solving problems in computer science, which is decomposition. First class in computer science that you will talk about taking a problem, breaking it into parts, solving each part, and then being able to quickly recombine the solutions. And the intuition is that if you have problems that are fairly small, each of them is very easy to solve. And if each problem is fairly independent or insulated from the others, then it can be solved by itself and the solutions can be recombined easily. So one intuition is conveyed by this example here, which is a little navigation task. You might imagine an agent that wants to plan a path through this environment. Each of the cells is a state that the agent might find itself in, and the agent can move up, down, left, and right. And so if the agent were able from each room to know how to navigate to the hallways, then in order to get anywhere else in the environment, the problem can be decomposed into getting to a hallway and then getting from there to some other place. And these are fairly independent problems because these states, the hallway states, insulate one room from another. You might also notice that in an environment like this, there may be regularity. So some of the rooms might actually look similar to each other, and we would like agents to be able to exploit that. Now, how does this translate into learning? Well, we can think of the problem of hierarchical learning, where now the agent doesn't really know the environment, but is able to interact with it. It could learn how to solve smaller problems, like how to navigate in each room, and then how to recombine these solutions. And again, a further intuition is that if you have an environment that might change over time, for example, because of non-stationarity, solving a subproblem might be stable over time, whereas the entire environment might actually require a different solution. So for example, the agent might be interested in one room today and a different room tomorrow, but if it has these independent solutions, it could track. And it doesn't necessarily need to relearn them. Now, this is very much an intuition that comes also from cognitive science and from animal learning, where we often learn some skill, for example, how to make coffee, and that skill remains even if conditions change. For example, you might buy a new coffee maker, you still know how to use it. We would like our reinforcement learning agents to have the same capability, so I'm going to talk about how to translate these ideas into reinforcement learning. Of course, in reinforcement learning, the agent's goal is to maximize long-term expected return. And so the idea is that the agent is going to learn some options or sub-policies which can be called to act. And it might also learn some models, jumpy models or temporally extended models that can help the agent in doing some planning. So I'm going to spell out a little bit these definitions now and then discuss how we can formalize the problem further and obtain stronger results than what we had so far. So what's an option? An option, you can think of it as a sub-policy. So in other words, it's a policy pi omega here that chooses level actions, but which has also an initiation and a termination. And the analogy really comes from classical AI and also from robotics and control theory, where you can think of some behavior as having a precondition, which describes when it can be initiated. It has some function that it performs, and then it terminates, leading to a post-condition or something that is true afterwards. So for example, in robot navigation, you might have a robot. If it has nothing in front of it, that's its initiation condition. It could go forward until it's too close to an obstacle, and that's the termination condition. So this is actually work that I've done more than 20 years ago now, which was formalized in my thesis and also in a paper that was published in 1999. How do we make decisions with options? Well, if you're familiar with reinforcement learning, the traditional way of thinking about it is that you have an agent that's in a discrete time environment. At every time tick, the agent takes an action. When we have temporal abstraction or hierarchy, this problem translates into a semi-Markov decision process where there are decision points that are unevenly spaced in time. And so you might imagine this sort of curvy trajectory here where each circle represents a decision point at which the agent changes its mind. The interesting thing is that in a reinforcement learning task, you can actually overlay these levels of temporal abstraction. So you could have primitive actions that are chosen at every time step. And then you could have these larger option jumps that are overlaid on top. An option essentially fixes the way in which the agent behaves for some period of time until the next decision point comes. Interestingly, options have been highlighted as part of human and animal decision making as well. There's even been some really interesting work from several people in neuroscience trying to identify neurocorrelates of options in the brain. These pictures are taken from a nice paper by Matt Bodwin, Mikael Niven, and Andy Bartow on hierarchical reinforcement learning in the brain. And so the analogy here is we're looking at, on the first row, at a flat reinforcement learning agent. Such an agent typically has a policy or an actor inside of it, as well as a value function or a critic, which guides the policy, provides gradients for the policy to move in. And so typically the actor is thought of as being associated with the dorsolateral striatum and the critic with the ventral striatum. We can do a similar kind of parallel for a hierarchical reinforcement learning agent. And this is what you see in the bottom row on the figure. The actor here has a little bit more structure because we're going to have a high-level policy which selects options. And then each option has its own internal policy. So you can see that the structure of this actor is a little bit more complicated. And the critic, again, is going to have a value function, but now this value function has to estimate the expected returns when the choices are made over options. And we can, again, find some neural correlates in the brain. So the actor in hierarchical RL agents is thought to have an extra little component here that is the dorsolateral prefrontal cortex. And the critic also has this extra component because it has to estimate values at different timescales, which is in the orbital frontal cortex. My understanding, not being a neuroscience person, is that these ideas of exactly drawing analogies between brain regions and hierarchical RL agents are still very much of interest and a work in progress. Now, just like primitive actions have models associated with them, options can also have models associated with them. For a primitive action in the Markov decision process, the model consists of immediate reward and the transition probability to the next state, which is the state on the next time step. For an option, a model will consist of the reward obtained until termination, expected of course, and the transition to a terminal state. And because now we have a temporal extent, this transition is going to take into account time as well. And the accepted way to do this is to essentially discount the transition, so to fold the discount factor into the transition. So there's one equation here on the slide which shows the reward option model. The option model basically says we're going to consider the reward on the very first time step. and then however much reward the option gets thereafter. And so the option continues to get reward so long as it is not yet terminated, because termination probability is beta omega, continuation probability is 1 minus beta omega. And we're going to take an expectation over these quantities. Now, what can we do with models? Just like in usual reinforcement learning, models can be used to do planning, and that can provide further benefits compared to using just options. And so I'm showing here an interesting example that actually also came from the work of Matt Botvinnik that looks at the kinds of gains that one can obtain by using hierarchical reinforcement learning in this little toy domain that I was showing you at the beginning. So here we have a flat agent. This is a usual reinforcement learning agent that's being trained, and it also does planning. This is the purple curve. The orange curve is an agent which has been provided with options that go to the hallways. And it can use these options both to generate behavior, so in order to move around in the environment, and also it can use the options in order to do temporal credit assignment. So for example, once the agent performs an option, it can update every state on that trajectory of that option with the outcome that has happened when the option terminated. And so credit assignment becomes both richer and extended in time. And you can see that options provide further benefit in terms of the speed of learning compared to flat agents. Now, when we also have models, we can furthermore do planning. So in other words, we can imagine a state, we can imagine taking an option from that state, and then updating the value function based on that imagined outcome. And using these models provides actually further improvements in this sort of blue curve. So this is the kind of gains that we can imagine obtaining from hierarchical reinforcement learning agents in terms of exploration, in terms of more efficient credit assignment, and also in terms of planning, which further improves the value function of an agent. But under what conditions really are these gains guaranteed? And so what we're going to do in the first part of this talk is focus on this question of efficiency in hierarchical reinforcement learning. And by efficiency, I'm going to mean both statistical efficiency. In other words, how can we learn a policy with few interactions with the environment, and also computational efficiency. So when we're doing planning, for example, what is the computational cost of that when we're using option models compared to using primitive action models? And I have to say that even though this field has been active for over 20 years now, and there's been experimental success, not just in toy tasks, but also in some larger applications, such as robotics applications, theoretical results are still quite few and far between. And so part of what I'm going to do today is try to make some steps towards hierarchical reinforcement learning theory. And in particular, we're going to try to highlight how we can characterize the complexity of planning and learning for HRL methods. And that will further help us sort of pin down our intuitions about the kinds of environments where hierarchical reinforcement learning can help. And one of the things that I really want to emphasize, and perhaps if you can remember one thing out of this talk, this would be it, is that hierarchical reinforcement learning is not a silver bullet, but really it provides a trade-off. The trade-off is between the quality of the final solution that can be obtained, the sample complexity, so how many interactions with the environment do we need in order to learn a good policy, and the computational complexity in the case of doing planning. And very often, this trade-off means that we're going to accept final solutions that may be slightly worse for the sake of obtaining much better sample complexity and computational complexity. So if you have a very small problem, for example, you can just solve it exactly. You don't need hierarchical reinforcement learning methods. Or intuitively, if your problem has no structure whatsoever, for example, it's just a random MDP, then doing hierarchical reinforcement learning is not going to help very much. Regular reinforcement learning would be sufficient. But we would like to characterize the class of problems where we expect HRL to really help. And the intuition really comes from these examples that I've showed you. If you have subproblems that are well insulated from each other and also that repeat many times in an environment, then solving a subproblem once should really give you big savings. And if the problems are separate, then they can be easily recombined. So we had a recent paper at NeurIPS, work led by my colleague Zhang Wen from DeepMind, where we formalize this intuition and provide a model-based Thompson sampling algorithm that can exploit the sort of hierarchical structure, the subproblem structure, in order to be both statistically efficient as well as computationally efficient in terms of planning. Statistical efficiency is going to be studied using the formalism of regret, and computational efficiency is going to be formalized as per episode computational complexity under different variants of value iteration. So I would like to take you a little bit through this problem formulation now and explain our main results. And I refer you to the paper for details on the proofs. So for the sake of simplicity, let's consider finite horizon Markov decision processes where you have a discrete state space, discrete action space. The agent has some fixed initial state, there's a fixed terminal state, and finite horizon basically means that the agent is going to reach this end state in a finite number of steps with some probability. This is mainly for the sake of having a clear and easy theoretical analysis, and the analysis can be extended beyond this. We're going to consider two settings. One I'm going to call planning. In planning, the agent actually knows the structure of the MDP, which means it knows the transition probability and reward function, and its goal is to compute a good policy. In the reinforcement learning setting, the model is not known to the agent, and instead the agent is allowed to interact with the MDPM for some number of episodes, and these interactions can then be used for the agent to estimate a good policy. And so in order to understand this notion of what is a subproblem, we're going to consider partitions over the state space. So what's a partition? It means that we take the state space and we chop it up into pieces. And in this picture here, the states that are in the same partition are colored with the same color. Now, in this particular case, I'm taking an arbitrary state space partition. We're not really trying necessarily to say what is a good or a bad state space partition. Just consider that one of these is given. If we have a state space partition, this is going to take the large MDP and generate out of it what I'm going to call sub-MDPs. And so, for example, here, if we consider the black states, we can take a subproblem that contains the black states and all of the states in the rest of the MDP that can be reached from the black states, okay? These we're going to call exit states. So in this particular case, there's 2 yellow exit states and 1 purple exit state. These are the places where we can leave the black region and go somewhere else. We're going to call 2 sub-MDPs equivalent if there is a bijection between their state spaces, which preserves the same transition probabilities and the same reward at the internal states in this problem. And so, this is a little bit of a restricted case. Again, it's something that we can likely relax, but it simplifies greatly the analysis. So for example, in this case here, there is a set of green states and there's a set of orange states, and the transition probabilities among the green states are the same, the transition probabilities to the ones among the orange states, and the rewards are the same. And so we're going to call these 2 sub-MDPs equivalent. Do equivalent sub-MDPs have exactly the same optimal policy? Well, in general, that won't actually be the case, because the values that they assign to the exit states may be different, and those values actually really influence the optimal policy. So for example, you might imagine 2 identical rooms in a building, but for one room you want to exit on the right, and for the other room you want to exit on the left. And so the corresponding optimal policies would be different, even if the room structure is identical. Now, what does it mean to have hierarchical structure in a problem? Assume that you have any state space partition in an MDP. The state space partition is going to sort of induce sub-MDPs, and there are some interesting quantities about these sub-MDPs. If you think of them as sub-problems that you're going to solve independently. One interesting quantity is what's the largest sub-problem, right? What's the maximum size of an induced sub-MDP? We denote that by M. Another interesting question is how many equivalence classes of sub-MDPs are there? So intuitively, if you have a problem where many sub-MDPs are equivalent, you can solve an equivalence class for different values of its exits, and then you're going to have these solutions. You can just quickly recombine them. So we denote by K the number of sub-MDP equivalence classes. And then another interesting quantity is what's the total number of exit states. This is important because exit states are the places where these subproblems connect to each other. And intuitively, if you have only a few exit states, these are going to lead to a simpler high-level decision process. And so we're going to show our results as depending on these three quantities, and these are going to replace the usual dependence and the kinds of bounds that I'm going to show on the size of state space. And in particular, we're going to have very big improvements over standard algorithms that solve the base problem if we have hierarchical structure with respect to the state space partition. Hierarchical structure basically means that the size of problems that we have to solve is small, and the high-level problem is compact. Okay. What does it mean to have a small task at the low level? It means that each problem is as small as possible, so M is as small as possible, and we have many equivalence many sub-MDPs that are equivalent. So in other words, the number of equivalence classes is small. At the high level, having a compact structure means that the number of these exit states, which sort of define a high-level problem, is much smaller than the size of state space. So just to make this a little bit more concrete, if we consider this rooms example, the number of exit states is 4. The exit states are just the hallways, and so high-level problems can be defined as circulating in between hallways. Equivalence classes, well, each room is really different, so each room is its own equivalence class, so we have 4 equivalence classes, and M, which is the size of the largest room, is 31. And so in this particular environment, even though it's been used in hierarchical reinforcement learning quite a bit, we don't really satisfy both of these requirements of a hierarchical structure in the sense that, yes, the high-level problem is small, but actually we do not have very much repeated structure in the environment. So let's try to think of, just for concreteness, of an example where this kind of structure might occur. So consider that you have a building that has floors and rooms, and you have a robot in this building that wants to collect garbage. So the goal is to maximize the amount of trash collected before the robot exits the building. And the building has big L rooms, but each of these rooms can be divided into different regions that define the robot's state. And furthermore, let's assume that the rooms are of different types. So for example, you might have conference rooms, individual offices, restrooms, and kitchens. And so now we have 4 room types. And imagine that each room of a particular type actually has the same division into floor tiles, right? So it has the same size and the same structure in its exit and the similar location of its trash can, right? And so now these room types become these sort of classes of equivalent sub-MDPs for the robot. And so in this example, we think of the maximum number of regions in a room as M. The number of room types is K. The number of doors in the building is the size of the sort of the exit states. These are the places where the space regions communicate among each other. And of course, the building might have many, many, many regions because there may be many rooms. So how are we going to take advantage of hierarchical structure in a HRL agent? To do this, I'm going to use a very general and quite widespread technique called posterior sampling for reinforcement learning. In posterior sampling, you typically have some prior P0, which reflects existing knowledge about an MDP. We have a planning algorithm, which I'm going to call plan. We have a sampling function, which I'm going to call sample. This is used to sample problems from a distribution over problems that is in the agent's head, and an inference algorithm called infer. And so this view is very much a Bayesian view, where we are assuming that there is a distribution over problems that the agent could find itself in. This starts with the prior. At every episode, the agent is going to sample a problem from its distribution that it maintains, is going to plan using the planning algorithm, obtain a policy, use that policy over the next episode, and obtain a data set. And then this data set is going to be used to update the distribution over problems. And so the infer step, this sort of update of the distribution over problems, is often a Bayesian update. Now, how do we inject the sort of hierarchical structure into posterior sampling? There's really two places where this can be captured. The first one is through a prior over problems, P0. And so, for example, we might assume that these problems only include MDPs that obey hierarchical structure. And so in our case, this robot might already know which rooms in a building have the same type, maybe because it's been sort of provided that information by a designer ahead of time. We're also going to discuss in a minute that the planning algorithm itself can be sort of adapted to the use of options through and models of options. So the first result that we derive in the paper is a regret bound that essentially says that if we have a prior that exhibits hierarchical structure defined by a maximum of M states per sub-MDP and K sub-MDP equivalence classes, then the Bayesian regret can be bounded by two terms here, okay? And the first term is really regret that comes from suboptimal planning. So every time that we are asked to solve our MDP for every episode, we may not do exact planning. We may incur some error epsilon. And so big T is the number of episodes. And so this part here is really under the control of the planning algorithm. The second term here is due to learning. And I'm not going to really go into the details of this, but I want to highlight that normally these kinds of terms depend on the size of the state space. And that dependence on size of state space is actually replaced here by a factor of m square root k. So this now depends on the size of the maximum problem and the number of equivalence classes or problems that we're going to have to solve. And so this result is actually a really big improvement if this sort of hierarchical structure exists. Now we're going to talk a little bit about planning and how to do efficient planning in this kind of setup. And again, we're going to discuss the fact that if we have repeating sub-MDP structure, we might be able to use this to improve the computational efficiency of planning. So imagine this problem that we discussed at the beginning, the sort of black states MDP. There are some states that are highlighted here in orange, which I'm going to call the start states. These are actually the states through which the agent can arrive into this sort of black partition. And the exit states, the ones that the agent uses to exit the sub-MDP, are essentially defining a termination condition. And so one way we can think about this is that we're going to have different values that we can assign to these exit states. And each of these values might generate a different optimal policy for when you are within this sub-MDP. And we're going to call an exit profile a vector that assigns a value to each of these exit states. One way to think about it is that these summarize whatever we believe about the outside structure outside of the sub-MDP. So if we now solve the sub-MDP independently, what we essentially generate is an option that starts at the start states and goes to the exit states, and which is roughly optimal with respect to both the rewards that we have in here, as well as the specified exit profile. And the termination condition is going to be given by the exit states. So now we can consider a hierarchical planning algorithm. I'm going to call this planning with exit profile, where we're going to induce options, and then these options in turn are going to generate a high-level MDP, where we're going to only think about going between these states that transition between these problems. And so just to make this a little bit more concrete, if we consider the entire big problem over here, the sort of MDP that we're going to consider at the high level goes in between these sort of states that connect the different subproblems. So here, for example, state 4 is a connecting state. It will be in the high level MDP, but this MDP might actually be quite a bit smaller than the entire problem. Its size is basically equivalent to the number of exit states. And the action space in this high-level MDP is going to be the available options. And so our planning algorithm is basically going to take as input a set of exit profiles. It's going to generate options based on these exit profiles and then plan with the corresponding option models in the high-level MDP. And under very mild technical conditions, we can actually show that this computes a near optimal policy quite efficiently. I'm going to show you this in just a second. But before, I just want to highlight that in this particular example here, we kind of used this exit profile idea just by luck without really calling it this. So the way that this example was originally structured in the options paper, we had some values assigned to the hallways, and in particular, the agent always had one hallway through which it wanted to exit. That one had a high value associated with it, and the other hallway was devalued. And so that gives us exit profiles. And for each of the rooms, essentially, we learned options that correspond to two different exit profiles that value highly one hallway or the other hallway. Now, this planning with exit profile algorithm would compute the options within each room, but then would also plan only in between the different hallways, so only plan using the option models that jump in between these exit states. In terms of results, which are detailed in the paper, the regret bounds and the computation per episode are summarized in here. The first row indicates what happens in the case of flat agents. These are existing results in the literature, and you can see that there's a dependence on the number of states. When we use posterior sampling that sort of highlights hierarchical structure, we obtain a dependence that's not on the number of states in the regret bound, but on m square root k, so size of the largest subproblem times square root of the number of equivalence classes of problems. And so you can obtain a big gain here if the MDP really has hierarchical structure. If we use the planner as the sort of hierarchical planner, then we can further reduce the computation time per episode, which no longer depends on the number of states, because now we're going to just solve the individual subproblems and then solve a problem that jumps around exit states. And so we can further obtain reductions in the computation per episode. But there may be an extra regret that is incurred. This is because, of course, the planner now depends on the quality of the exit profiles that we have. And so, of course, the more fine-grained these exit profiles are, the better the quality is going to be. Now, one thing that I want to highlight is that these results that we have hold for any decomposition of an MDP into sub-MDPs given by a state partition. And in the paper, we do not discuss the issue of how to get good decompositions, but essentially the bounds that we have could in principle be used to guide a discovery algorithm that tries to figure out a good decomposition of state space. And again, I want to emphasize is that these bounds show trade-offs between solution quality, computation time, and sample size. Of course, if the problem has no hierarchical structure, then you can't get gains out of these methods. And so you really need to exploit something in order to for this to be interesting. We are now thinking about extending these results both to using approximate bijection, so a looser notion of what equivalence class means, as well as using function approximation. So since I have a little bit of time left, I'm going to also discuss the issue of generalizing option models a little bit to something that is slightly more general, called a general value function. And so in the case of reward models, we have seen that we can think of the internal workings of a model as having some rewards and then some accumulation over time that's controlled by the options termination condition. We can actually generalize this notion to a value function that depends on a general cumulant that doesn't really have to be reward, could, for example, be a vector or even a matrix. And the continuation function, just like in the case of options, might in fact not be uniform over the entire state space or constant over the entire state space, but it might be state dependent. These ideas originated in a paper that I was fortunate to collaborate on the Horde architecture from 2011. And are currently being explored in various guises, for example, by Martha White's group, Adam White, and other people as well. One interesting example, especially from the point of view of neuroscience people that may be listening, is the connection of these general value functions to successor representation. The successor representation was introduced first by Peter Dayan, and it represents the discounted state occupancy of an agent conditioned on a policy. And my colleague Andre Barreto generalized this with his collaborators to the notion of function approximation by considering these cumulants to be feature vectors. And so now what we can essentially get is not just a model for what happens when an option terminates, but conceptually, we could get a model of what happens as the option is executing. The option has a fixed policy, and these feature vectors accumulate during the option execution. There's an interesting special property in the linear case, which is that if we consider linear combinations of these cumulants using a weight vector W, we can actually recombine very quickly value functions that are estimated for the different cumulants in a linear way. And so essentially we can compute the value function of any linear combination of cumulants, zero shot. And so that's a property that we can use for doing very quick policy evaluation. And Sam Gershman and colleagues have looked at the connection of this kind of formalism to dopamine. And in fact, there's a hypothesis that maybe dopamine, in fact, does give a vector valued signal for updating such representations rather than thinking of this just as a scalar. So how can we leverage these more interesting models in the options framework? Well, the analogy that I would like you to draw is imagine that you have options that optimize for some subcall, okay? And so if you had, for example, a piano, you might imagine an option as being, being able to hit any particular key, okay? So I might have an option for do, an option for re, and so on, and I can have a set of options that are individually able to hit a key on this keyboard. But hitting individual keys doesn't lead to very interesting music, right? In order to get interesting music, you need chords, and you might need to have chords where some keys are emphasized, they're hard, and others are soft. Okay. And so this notion of weighted cumulants is essentially like a notion of chords. So we're going to have a linear combination of individual cumulants or individual keys. And these strengths, these weights, can tell us if we want a lot of that cumulant or very little of that cumulant, or maybe none at all. And in fact, these weights, of course, can also be negative. So the agent might try very hard, for example, not to touch some key, because then there's going to be dissonance. So now, how do we actually generate behavior using this kind of idea? we're going to use a general formalism that's similar to policy evaluation and policy improvement, called generalized policy evaluation and generalized policy improvement. And the intuition here is that we can fix a set of options that corresponds to a set of sub-policies. We can compute their successor features, and then generalized policy evaluation is just a matter of using these successor features to evaluate linear combinations of cumulates for which the options have been trained. Okay, and so you can this sort of grayed box at the top here is your set of options. We can compute their values with respect to any linear combination of cumulants from a cumulate set for which these have been trained. Now, for any particular linear combination, we might actually want to try and improve the behavior. So rather than calling the options, we might try to generate a new policy, which is improved. And of course, we can do that by policy improvement. We call it here generalized policy improvement because we might do this with respect to different tasks. So we've explored this idea in a recent PNAS paper and also in a NeurIPS paper from 2019. And one of the interesting conclusions that we come to is that this approach can allow us actually to generate behavior that is much richer than using options in a call and return fashion. And so for example, here we have a task, there's a circular arena. There's a little agent here that's trained to go in these black directions. And so it has some options colored in red, blue, and green that can take the agent roughly in this direction. But by using these sort of weightings among the options, we can generate behavior that goes really anywhere in the arena. Okay, and in particular, the agent can learn to go away from the actions that correspond to these options if, for example, its reward function is aversive to these directions. And so this is how we can generate some of these yellow slices that have very little overlap with anything else. What is the empirical impact of this in terms of the speed of solving problems? Well, we have here the red curve is deterministic policy gradient. This is a good flat agent. The green curve is an agent that just uses its options in call and return fashion, so in the sort of classical way. And as you can see, it's faster at the beginning and plateaus at a worse solution. Again, this is the sort of quality and speed trade-off that we have mentioned before. And now we can actually use different option keyboard players with different numbers of options. And as we increase the number of options, the performance, the end performance gets better. We still have significant gains at the beginning. And if we actually allow the agent to redecide which options it's picking at every time step through these combinations of cumulants, if it learns how to do that, it can get to really quite good performance. This is this dark blue curve. And here, of course, the options have an extra cost for their training. And so we're accounting for that in this sort of gray area. But you can actually see that even with this cost sort of taken into account, the option, the hierarchical reinforcement learning agent is significantly better. So I'm going to wrap up the talk just to say that we now have some very, very general tools for reusing policies and predictions, and that can be very quick to provide solutions to solve problems. Some of these results that I've showed you are zero shot. Other ones are actually obtained in the paper with very, very few samples. And one of the things that I really want to emphasize is that rather than thinking in purely hierarchy terms, we can in fact sort of diversify our thinking a little bit to conceive of modularity and compositionality. And so these agents can solve different kinds of subproblems, possibly overlapping subproblems, and combine their solutions in more interesting ways, but always with this idea that there's going to be a trade-off between the solutions of quality, sample complexity, and computational complexity. There are many, many important research questions for those in the audience that are thinking about this. The two that are most on the top of my mind is, first of all, evaluation. How do we actually quantify the performance of hierarchical RL agents in a good way, looking not just at returns, but also some other capabilities, for example, or qualitative measurements of the agent's behavior? And then the problem of discovery. How do we actually discover good hierarchical RL representations? So I'm going to stop here, and I am happy to take any questions.
Thank you so much, Doina. I'm sure that everybody's joining me in clapping hands in front of their laptops. We have wonderful questions from the audience, and you were perfectly on time, so we have a few minutes. The highest voted question is from Harm, who is at the MSR in Montreal. He asks, do you believe there are other modes of decomposition that are important besides a hierarchical decomposition based on state partitioning? If so, which are those?
Yes, that's a great question. And there's definitely better things to do. So for example, when we have function approximation and we have features, one way to do decomposition would be, for example, to take the feature space and do random projections, and then perhaps solve the problems that are defined by those random projections. Or, of course, one could imagine taking subsets of the features and solving problems relying on those subsets of features. So the reason we stuck with state partitioning is that from the point of view of theoretical analysis, that greatly simplifies things. But I think there's actually a lot of richness in this area. And I know Harm has also done wonderful work in terms of decomposing reward functions and using those kinds of ideas. So I think there's just a lot of opportunity to think about more flexible ways of decomposing a problem and recombining the solution.
Thank you so much. The second highest voted question is by Jalal Arabnadi, and they're asking, would it be possible to use the idea of attention mechanism in deep learning that decomposes the task space to decompose the state space in the proposed sub-MDP?
Yes, again, great question. Absolutely, I hope that attention. So there's a really interesting interaction, I think, between attention, this idea of temporal abstraction, and sort of defining, for example, affordances, which mean, you know, which of the options, for example, would be actually available at a particular configuration in observation space. And I think this is a place where there's a lot of overlap in ideas. There hasn't really been that much of a clear connection that's been established. You know, partly also because I think some of the ideas are more focused on empirical solutions to very particular architectures. But I think it's a very fertile area for research, and for sure there would be the opportunity to use attention mechanisms to, for example, learn some of these partitions, maybe not as partitions, so not, you know, using hard attention, maybe using soft attention. I think there's a lot of opportunity to explore there. And I'll just give a quick shout out to my PhD student, Katja, who's been thinking about some of these questions as well.
Yes, we're excited to work with Kimia in the summer. So, the third question is also by Harm. Harm asks, if options or structures are not given beforehand, do you believe HRL has an advantage in terms of sample efficiency as well? And if so, what is the basis for this advantage?
Yes, so in the results that we have, what is provided at the beginning is a state space partition, and it could be anything, right? So it could, for example, be random. So the cost of computing that partition is very small. And then, of course, the learning and the planning algorithm learn the subproblems, and they learn the high-level solution. And we don't really, you know, think very much about this being a phased process. So in principle, if the problem has, if the partition, the initial partition has got the right structure, we obtain these gains even if the solution is not given ahead of time. Now, how difficult is it to compute a partition that is good? This, I think, is an open problem, but I think, again, there are kinds of environments where this will be efficient. And I'm thinking specifically about the continual learning setup, where maybe the agent has a very, very large environment where it can get, you know, there's not a way really to handle the environment as a flat thing, and the agent can sort of abstract away and find these partitions in its head, right, at a feature level rather than a concrete level. But yes, I believe that this is possible to do even without doing any pre-training.
Thank you so much, Doina. I really appreciate it. There are other questions that I will send them your way for later on. Thank you, everyone, for being here. I would like to hand it over to Katja Hofmann, one of my favorite collaborators ever. Katja is a principal researcher at Microsoft Research in Cambridge, UK, where she leads research at the intersection of reinforcement learning and gaming. Take it away, Katja.
Thank you so much, Ida, and congratulations, Doina, to such a fantastic talk. It's my great pleasure to welcome you to the next section of our program today, a reinforcement learning debate on RL and the theory-practice divide. Our speakers will be Yoshua Bengio and John Langford, and I will introduce them in more detail shortly. First, just a few words about how this debate will run. We'll kick off with brief introductions of our two speakers, as well as their opening statements. After that, I will kick off the debate with a few questions that are prepared. And most importantly, this is an amazing opportunity for you to engage. We will be looking out for your questions in the Q&A. So start submitting them now and throughout the debate, and we will be selecting the ones that we can ask directly to our speakers. With that, without further ado, I want to introduce Yoshua Bengio, and hopefully he will be able to share his slides while I give the introduction. Dr. Yoshua Bengio is professor at the Department of Computer Science and Operations Research at the Université de Montréal and scientific director of Mila. I was intrigued to learn that he was actually born in Paris, France. Since then, he has obtained degrees in electrical engineering and computer science from McGill University, and he is recipient of a wide range of awards and prizes. Just to name a few, he is a Fellow of the Royal Society of London, a member of the Order of Canada, and a Fellow of the Royal Society of Canada. He also received the prestigious 2018 ACM Turing Award jointly with Geoffrey Hinton and Jan LeCun for his fundamental work on deep learning. Apart from reinforcement learning, on which we will hear a lot more today, Yoshua thinks deeply about AI and how other scientific contributions could potentially address the challenges of COVID. And he's also involved in scientific publishing processes and tries to understand how this process is shaping at the moment and in the future. And if you want to read more about his thoughts and what is currently on his mind, he does have a blog under yoshuabengio.org. With that brief introduction, I want to now hand over to Yoshua for his opening statement. Yoshua, over to you.
Hi, Katja. Thanks a lot for the introduction. So I would like to give a 1-hour talk, but I have only 5 minutes. I'll try to be brief. My title is saying, Bringing System 2 Understanding into Deep Reinforcement Learning towards Learning Abstract Entities and Abstract Actions. So I've talked a lot in the last couple of years about higher level cognition and System 2 representations with the deep learning perspective. In other words, how do we represent, for example, images and videos? And one thing that my group has been moving towards in the last few years, of course, is like many people in our community, is reinforcement learning. And so what I want to emphasize today is the crucial tight connection between the representation of abstract objects in the world obtained from perception and the representation of abstract actions, very similar to what Doina has talked about with options. So, just quickly about the System 2 aspect. Essentially, our brain contains a lot of knowledge. Some of it we can verbalize, some of it we can't. And I'm just going to, say there's these two kinds of knowledge, the verbalizable and not verbalizable. And the nice thing about the verbalizable knowledge is that by looking at the way we express it with language, we get a lot of hints about the sort of dependencies, the sort of constraints, this is sort of a priori structure that is in our corresponding internal model of the world for that type of knowledge. And so this is something that I've been after recently, and there's a paper I put out on arXiv, which is the last one with my name on it, I think, with Anirudh Koyal on this, that I encourage you to have a look at. Now, there's really something important for machine learning in thinking about these questions. Doina talked about sample complexity. but it's even more than just sort of a general sample complexity, is sample complexity when things have changed in the world. And we can look at humans for inspiration there. When we are faced with something unusual, we don't follow our habitual routines. We think hard to solve problems, plan, and find novel solutions that combine existing pieces of knowledge. And so I think that although a lot of progress in RL and deep RL has been made, mostly it's on the system one side. It doesn't use a lot of these, I think, inspirations we can get from humans about organizing high-level knowledge. One of the maybe strongest assumptions I think that can drive a lot of this is what Bernard Schopkoff and collaborators call the independent mechanisms assumption, which says that we can decompose knowledge into independent pieces, and these pieces correspond to the causal structure in the world, how different entities are related to each other causally. And so that's really about the dynamics of the world. If we do a good job of capturing these causal mechanisms, then we can get a very fast adaptation to changes in distribution due to interventions, when something changes due to an agent doing something, or even zero shot adaptation. You have to keep in mind that this needs to be combined with system one in many ways that I want to have time to explain. Let me move on to my last slide, which is the biggest one. So what are we missing? I think many things that have been discussed potentially separately, but I think we need to put together. So my group has worked a lot, and others have worked a lot about how do we go from low-level perception to high-level causal variables, entities, objects, and so on. But you need to do this at the same time as you learn the corresponding abstract actions. And so there's a nice thing that comes from thinking about it from the causal perspective, which is abstract actions correspond to interventions on these causal variables, or the abstract causal variables, think of them as properties of entities in the world. And that's a very strong connection, right? It says that a good way to think about abstract actions is that they're very their effect is very local in the abstract representation space of objects in the world. And then in addition to these two things, like representing causal variables and abstract actions, you need to also learn the causal dynamics, which link these two things together. In other words, if I do such abstract action on such entity, what will be the outcome? And finally, you're going to need some system one ingredients as well, in particular for inference. Inference from observations, inference needed for planning, inference needed for doing counterfactuals and performing causal credit assignment. Finally, there's very strong connections between this whole discussion and natural language, because once you can represent things at this abstract level, you can take advantage of the fact that there's a simple mapping between those entities and those abstract actions and language. Essentially, it's almost like a one-to-one relationship. And then not forgetting that the way that we want to test these things and even optimize them has to do with out-of-distribution generalization and speed of adaptation. So I'll stop here. I think I probably went over my time already. Thanks.
Thank you so much for sharing your thoughts here, Yoshua. Next, a brief introduction for John as he gets ready to present his opening statement in turn. John Langford is a partner researcher manager at Microsoft Research in New York. I was again intrigued to learn that he was born in Lebanon, which is in Oregon in the US, and holds degrees in physics and computer science from the California Institute of Technology and Carnegie Mellon University. John is on a mission, a drive to make machine learning more and more practical as he sees the field shifting from an academic discipline to an industrial tool. His many research contributions have focused on areas that in many cases involve reinforcement learning, and many have been practically demonstrated, for example, in his contributions to Walpole-Wobbett. He coined the term contextual bandits and has made many fundamental contributions to the field of reinforcement learning. Like Yoshua, John is maintaining a blog, this one under the address of hunch.net, where he shares his thoughts, again, for example, about the publishing process in his current role as president of ICML, digital contact tracing in the context of COVID, and very relevant topics, both in research and the wider society. With that brief introduction, I want to hand over to John, looking forward to hear your open statement.
Thank you. So I wanted to start by sort of describing 3 different reinforcement learning research styles that I see when I look around at the field. One of these is kind of the adventure style, and the idea there is that you have a mountain and you go and you climb the mountain, and you know, that's really cool, a lot of fun. And another one is more application style, so you're trying to actually make reinforcement learning create valuable and useful things in the real world. That's also a lot of fun in its own way. You can see the impact of what you're working on in a much more direct way. I like that a lot. And then a third style is more sort of fundamentals driven. You think about counterexamples to, like this figure at the top here is a counterexample to inverse kinematic style state definition. And the equation at the bottom is an optimization which has a provable state abstraction property. So these are 3 different styles that you see when you look around the field of reinforcement learning. And of course, there's feedback between these styles. And I intentionally drew the applications and the fundamentals as being near to each other, because my experience is that if you're working on applications, you really want things that are going to work reliably. And a careful understanding of the fundamentals is essential in creating a system that can really work reliably. So there's a tight connection in my mind there in terms of creating a successful applications, and also to some significant extent in informing what fundamentals you should work on. Okay, so this is about research styles. I also wanted to spend a little bit of time talking about where we are at, and I kind of have a cartoon view of this, but I think it's a useful cartoon. There's sort of different levels of intelligence that you see in the natural world. So a worm can kind of learn to seek and avoid. A hunting spider can plan, and it has vision sensors that can plan its route to get to various places. A wolf can cooperate. It has a large memory of where it's been and what it's done. And then, of course, at the human level, you see things around communication and abstraction, which seem pretty unique to humans, even compared to our nearest relatives evolutionarily. So this is kind of a cartoon view of things. And now the question is sort of where are we at, right? So I can think of this as sort of basic reinforcement learning is the worm. Advanced reinforcement learning is sort of the hunting spider. And then there's more speculative things going on around cooperation and large memory, and then even general intelligence. And then where we're at right now is for basic reinforcement learning, we have a system where you can go and create your own reinforcement learning agent and start doing things, right? So you go do that today if you wanted to. There's a lot of fun stuff going on around the cooperation, large memory, communication, abstraction. And then the action in reinforcement learning in my mind is really around this kind of combination of you have a rich sensor, you need to be able to plan or succeed. How do we effectively do this in real settings? Okay, so let's think about that just a little bit more. In reinforcement learning, there are kind of 3 different key problems that come up. One of them is sort of the credit assignment problem. It's which move lost the game, or did I turn? Was it right to turn left or right? One of these is exploration. One of these is generalization. So in exploration, you're trying to gather the information that you need in order to succeed. In generalization, you're trying to just generalize from past experiences to future experiences. And of course, there are combinations of these. If you do exploration and generalization, you do contextual bandits, which is where we have a deployable system. If you do exploration and credit assignment, this is tabular MDP learning. This is like the E-cubed algorithm, RMAX, if you're familiar with that. And then if you do generalization and credit assignment, you're doing policy improvement style algorithms. There's been a lot of fun around these, and this is kind of a workhorse throughout reinforcement learning. And now the action in my mind is really around the combination of both of these. If we can, of all three of these, if we can solve all three problems simultaneously, then I think that we are approaching very closely what the hunting spider level of intelligence is. So I've seen a lot of work. There's some out of my lab, some from other labs as well, which is trying to address all three of these simultaneously. And my expectation is that in the next couple of years, we will see rapid progress in this area, and we'll come to look back on the era before we knew how to solve all three of these problems. It's sort of it's like the decision tree era of supervised learning. It's something that's kind of a useful idea that people worked on, but maybe we can do much more now. So I wanted to leave you with some pointers. There's the personalized service, which I mentioned, where you can go and get your own reinforcement learning agent. There's Vocal Wabbit, which has a lot of algorithms for contextual bandits, which is widely used. There's several latent state discovery papers where we're discovering latent state and addressing that kind of trifold problem. And then there's a tutorial we did recently for Fox on the theoretical foundations of reinforcement learning, which you may be interested in taking a look at. All right, thank you. Looking forward to questions.
Fantastic. Thank you, John, and thank you, Yoshua, for sharing your initial thoughts here. I want to jump right in with the first question on where you see the next steps to advancing reinforcement learning. Yoshua, you very much focused on advances needed in what you call system 2, so focusing on causal models, inference in these models, as well as explainability to drive advances. Whereas, John, you were emphasizing that we need to bring together generalization, exploration, and credit assignment. So on the surface, these seem to be very distinct and different from each other. Who would like to take a start and see, are there very large differences in your views, or do you see connections that maybe are hidden under the surface?
So there's differences in the words, but I think that and perhaps an emphasis, but I think there ends up being a lot of sharing in terms of what you are actually doing. So I could re-describe some of what I talked about, like the latent state space. I could say, look, I'm learning abstractions of the latent states and the dynamics operators, and I'm planning inside of these latent states in order to reach the frontier of experience. And so now the language starts to sound very much more similar to what Yoshua was working on. Yoshua,
so I guess there's maybe a difference in emphasis. I put a lot of emphasis on representation, and I mean, connected to this is representation is really about inductive biases in general, right? So I feel like I take the no free lunch theorem seriously, that we need to put in some sort of inductive biases. They don't need to require a lot of bits to be expressed, because they have to fit in your genes. But they could make a huge difference in terms of generalization for the kinds of problems that humans solve. And so, discrete representations, which is the heart of deep learning, is of course an example of that, but it's only one out of maybe a dozen such inductive biases that I think we need to put in. And working on the questions of like what should we optimize, what kind of guarantees can we get, are important. But I believe I'm putting a lot more emphasis on the representation and inductive biases aspect. Maybe that's one way to see a difference. I don't know if you agree with that. Do you, John?
I think I agree with that, and I think this is maybe a first point of debate.
Cool.
I regard what you optimize as more fundamental than what representation you use, which you optimize over. Because if you have a bad representation and you optimize for the right thing,
well, asymptotically,
kind of useful. Asymptotically, but the vice versa, I think, is maybe it's not true at all. So I think it's really critical we optimize for the right things. And so figuring out how to decompose some sort of complex problem you want to solve into the simple problems that you want to solve, such that their solution will give you the overall solution, the global solution. That is often, I think, very central to a lot of the work that we've done.
No, I do care about what you optimize, don't get me wrong. In fact, one of the questions I spend a lot of brain cycles is, what should we optimize for exploration? I don't think it's obvious at all. And then another thing that I care about in terms of what should we optimize is, if you want to obtain the sort of optimal decomposition of knowledge, which I think the independent mechanisms theory suggests we should have, what should we optimize? Because it's not like this theory doesn't tell us what to optimize explicitly. And so there are a lot of open problems in what are the right objective functions. As soon as you move away from like the standard, either a standard supervised learning or the standard RL framework, where, well, we know what we're optimizing, it's pretty obvious. But you move to things where you have exploration or you have non-stationarity or whatever, and then it's not so clear anymore.
Mm-hmm. I agree with that.
It sounds like there is quite a lot of agreement between the two of you, despite some differences in emphasis here. Maybe to be a little bit more provocative, you both seem to place a lot of bets on model-based reinforcement learning. But given the successes that we have seen recently, or empirical successes that we've seen in model-free reinforcement learning, why is model-based RL even necessary?
Well, I think John had it. We have to go beyond the worm. Go, John. It's your.
Yeah, so I think that model-free reinforcement learning basically cannot succeed anywhere that you have a truly sparse reward situation. You need to be able to model the dynamics and explicitly explore the dynamics in order to actually explore the relevant part of the world, in order to discover how you can what you can optimize for. And so a model of some sort is just necessary for that. It may be implicit, it may be explicit, exactly what the form of it is. It may be something which is verbalizable or just parametric, but there needs to be some way to cause your system to explore broadly, and ways to introspect about where you have not explored, so that you can actually gather the information you need in order to learn.
Yeah, and I would summarize it to just two words: sample complexity. And where it does matter a lot is when you have a changing world. The underlying causal mechanisms of the world don't need to change, but we are, in different countries, we meet different people, we have climate change, all kinds of things change. And we need learners that can quickly adapt to those changes. And that we don't have so clearly with model-free RL. So you need some ways of capturing what is shared across all of these different environments, and that's the promise that model-based RL can bring. Now, maybe there are other ways of doing it. Okay, I'm not sure the brain does exactly the kind of model-based RL we are thinking about, but I think it does something of that nature.
Fantastic. You both seem to align in the sense that model-based reinforcement learning is really needed to get us to the next level in terms of what reinforcement learning is able to do. But more concretely, where do you see the most promising directions, the most promising ideas in order to get us to that point? And maybe, John, do you want to take that first?
So we've had a research program for the last several years where we've been trying to understand, I guess I could say, the mathematics or the fundamentals of how you can actually reliably build a latent state space. And I think that we're not entirely there in terms of understanding, but we do understand there are fundamentals. That many strategies people have proposed do not work. That some strategies do work. Some strategies have limitations, and so I feel like it's important that we flesh out these fundamentals a little bit further in order to broaden the nature of latent states that we can deal with and things like that. I also feel like it's essential that we take some of these ideas and really try them out in the real world, or at least push them into applications and see what the flaws are in our theory, so we can repair that and improve from there.
Yeah, I agree with that, but I'm going to be more specific. I think that in the kind of world in which we live, directly modeling the dynamics of, because dynamics is the most complicated part of a model in the model-based RL. Modeling the dynamics directly, like in pixel space, is hopeless.
I agree.
And so that's why John was talking about the latent space. And you can see this by the fact that many phenomena, in particular the causal structure as humans describe them with language, can be summarized, could be presented, described with a few bits at the abstract level that we use words for, but at the pixel level, you can't. It would take hugely more parameters if you want to describe these things. So that's one thing. And what this tells me is also, okay, so we need a latent space, but more than that, we need to put structure in the dynamics in the latent space. It's not like a big neural net that takes the full description of the state at t and maps to the full description of the state at t+1. This is not how humans think. And this would still be like a hugely complex model that doesn't look like how humans understand the world. And it also does not exploit this independent mechanism story that I talked about. So what does the independent mechanism story say? It says that what you really want is to decompose knowledge into pieces that are independent of each other from a complexity theory, like information theory point of view. What does it mean? It means if you take the code, the parameters, or like you write the sequence of bits that describe one mechanism, one piece of knowledge, and you do it for another piece of knowledge, there's no gain in compression by concatenating these two things compared to compressing them separately. Right? Though there's no redundancy. So of course that's an ideal thing. And if you can do it, of course, you're going to gain in sample complexity. You want to be able to reuse the same piece of knowledge, just like when we write code. Okay, so how do we do this? I don't know, but a big part of it seems to be that we need to modularize knowledge, that we need to decompose it into these pieces. And then we need to have something like a tension mechanism to decide on the fly which pieces are needed to solve the next problem. So these are the kinds of questions I'm thinking about. But there are many other aspects that I think are important, including the connection between interventions and actions in RL, interventions in causality and actions in RL, which tell us something about the deep relationship between the causal variables in the latent space and the space in which, and the constraints that apply to abstract actions like options.
John, I'd love to hear your kind of further thoughts on this. You mentioned that a latent space is very important, but you haven't quite committed to any additional structure or form that this latent space should take, whereas Yoshua is very much emphasizing his belief that a causal structure is necessary and there are aspects of compositionality that need to be captured. I was curious to hear your thoughts on whether you consider that a convincing argument or necessary to making progress.
I think it's essential. Sorry, I'm agreeing too much, but I mean, the definition, what is a latent state? It's something which you can plug into a transition model, which is going to get at the causal structure of the world, right? And so how do you discover the causal structure of the world is inherently bound up in even in the concept of a latent state, right? So just to give a couple pointers to examples. So we have discrete latent states. That was the Homer paper. We have some generalization of that in the Flambe paper. We have discussion about rich observation linear quadratic regulators. That was a NeurIPS paper. There's a new one at ICLR talking about latent combinatorial state spaces and how we can discover them. There's more that needs to be done to really understand these, and I don't think we yet have a kind of a unifying principle. It's so far it's been like, oh, this seems like an important problem to attack. Let's try to attack that. Okay, here's a solution to that, and here's another one. And now we're reaching the point where we have enough examples that we can start fitting them, think about underlying principles and fitting them together and so forth.
Yeah, and maybe I can add something to this, which is something I've been thinking about recently, is that in my own work and in what I've seen in the community, as John was saying, people have been tackling little pieces of the problem, and no one has really had yet the ambition or the compute power and manpower or person power, sorry, to jointly learn all of the pieces, right? So what are the pieces? So the pieces are the encoder, if you want, that maps perception to abstract or a latent space. Another piece, well, you would have a decoder that goes in the other direction. Another piece is sort of like the option piece, right? So the abstract actions are mapped to low-level policies. And then another piece is the dynamics that we've been talking about. So nobody has been learning these three pieces together, and I think we need to do that. And I'm a big believer in end-to-end learning whenever we can do it. And now we have to find, what is the right objective function for this, and I have some ideas about that, but I think it's an open question. Can we do it? Like, I don't think people have had enough ambition to try these things. It sounds like it's too difficult to chicken and egg, but I think we should do it.
Definitely a very inspiring direction and problem. Before we turn to questions from the audience, there's one last topic I would like to touch on, and that is the connection between practical applications and both empirical and theoretical progress. John, you already briefly touched on this and mentioning that you think testing this out in practice is really crucial. Could you expand on where you see the kind of role of practical applications and their connection to research?
Yeah, so I think practical applications are incredibly valuable in terms of telling you where you sort of modeled the problem wrong. Maybe you did the wrong theory, or maybe your theory needs to be adjusted or needs to incorporate something else because there's some essential element that you missed. And so that's very important for sort of the foundations aspect of research. I think there's also, for me personally, I really like seeing the things that I work on actually get used, and so I'm super happy whenever we can actually do something great that is widely useful.
Yoshua, do we have any additional thoughts on this?
Oh, I agree with John on all these things, but I would add that in addition to applications, as sources of guidance to improve our insights and understanding for more basic research, I would say there's been a lot of work, and we need more on the training environments, right? So RL environments, in the designing them so that they would put the right challenges on our path to address the difficult questions that we haven't addressed yet. So, I'm involved in several of these papers in the last few years, but and I think it's a non-trivial question. If it's too easy, then maybe the researcher is sort of cheating and exploiting the specifics of the environment. But the good news is that we already have a number of these where no one knows how to solve those problems well. We may have different levels or something, and we can do the easy cases, and then none of the algorithms we have do a good job on the hard cases. So I think we are in good shape. Probably there's going to be more work coming in from there, because the interesting environments also help us. It's not just a challenge; it's also a debugging tool, right? So because we know the ground truth, we can compare what we learn with what we know should have been learned. This is something we can't do in real life usually. It could really help us speed up the research cycles.
Fantastic. With that, I would like to move to questions that we have received from the audience, and I'll be asking the most highest voted questions. The first is from Hari Teja Tatavarti, who is asking, how long do you think reinforcement learning would take to be widely applicable in the industry? And also, what areas do you think are most suited for RL applications in the real world?
So I think reinforcement learning is widely applicable right now, in fact. So there's several ways to see this. There's certainly a lot of problems which have a very much reinforcement learning nature, like machine-driven stock portfolios or ad choice and things like that. So those are essentially just solving a reinforcement learning problem. It's a very tricky one, and there's some extra complexities, but they have specialized systems that exist that do these things right now, right? So for like high frequency trading or things like that. In terms of creating more general value, because you might kind of doubt the zero-sum nature of high frequency trading or most distracting advertisement. In terms of creating more value, it's clear that reinforcement learning can be very helpful for sort of nudging applications. So if you want to help people support healthy habits, you could create an app that helps nudge them. Maybe they say, oh, you should take 10,000 steps today, or maybe say, oh, yesterday you did more, or things like this in order to help people support healthy habits. There have been applications in actual like online learning, the way that most of the rest of the world thinks about online learning, education. There's this personalized service that I mentioned, which is a system that is being used to personalize a lot of decisions of one sort or another, and some of those are very useful. Just like which part of the website do you want to go to next, things like that. There's no reason why a website should be dumb anymore. It can be smart. It can learn to surface the elements which are most relevant to the people who are actually trying to find whatever they want. So at this point, I think that the worm level of intelligence is actually pretty widely deployed and certainly more widely deployable. The more advanced levels of intelligence, I think, are not so widely deployed, but we can see these things happening. Katja has been playing around with games for Xbox, for example, right? And there's some possibilities there, which, fun to think about. And I can easily imagine other applications coming along as well.
Certainly a very exciting area. Yoshua, do you have any quick thoughts to add to this one, or should we move to the next question?
John did a good job. I would just add something that actually is very close to the heart of big IT companies, and that is natural language understanding and dialogue. And the reason I'm putting this there is because dialogue is a interactive thing, and it's difficult to deal with that interactive nature unless you really go to the tools for reinforcement learning. We can bootstrap with unsupervised learning and supervised learning, but I think to get the best fine-tuning, which is actually something we did in my group many years ago in a dialogue competition, really it helps to use RL. But I think we use the worm level RL then, and what I'm really interested in is the longer-term potential of RL and these more complex forms of machine learning that we've been discussing to tackle, huge applications like, natural language understandings. Like any small progress there is like revolutionary. And of course, things like machines that acquire information purposely. So one area that I'm working on right now is in drug discovery. In drug discovery, where you're going to iterate multiple biological or chemical experiments, is really like an interactive process where you get rewards later for having asked the right questions early on. So it's a form of active learning, and there you can really use the principles of reinforcement learning and the research in exploration and so on to make progress. And these could have huge impacts for everyone.
Fantastic. The next question is from Kimia Keterpal. She's asking, would love to hear your thoughts on what is the right setting for reinforcement learning agents to learn more closely aligned with how humans learn. Given humans do not learn in a single task setting and given evolution, etc., what do you think about continual learning settings as the right setting to learn in?
I can say a few words. Oh, go ahead, John.
Just in terms of research path, I think the full human level is in many ways beyond, it's just too big a step to us to do. So I sort of do think about this ladder of intelligence where you try to build up to more and more complex things. And so if I try to think about something which is sort of the hunting spider level of intelligence, then I think about a world where you have the same dynamics over time, or mostly the same dynamics over time, but the task that you want to solve in that world changes over time, multiple ways, and you need to solve a sequence of tasks, not merely one task.
Yeah, I agree. And as I alluded to earlier, not only I think that this is a real world issue, that we want robots or automated systems that can deal with new tasks, changes in the reward function, whatever, but it's even better than that. I think this is what you need to optimize. You need to optimize for the ability to quickly adapt to new tasks on the fly. And that may be the training signal that we need in order to discover, what is common across all these tasks. What is the causal structure? What is the right latent space? So I think this is very important. Now, that being said, I'm not a big fan of a lot of what is going on in that literature. For example, there's a lot of emphasis on, you're not allowed to store the past data because you're supposed to do online learning and you have limited memory. But like mammals have a big enough brain to store their whole life in their brain. So I don't think memory is a real bottleneck. I think, which is often like the way people think about in continual learning. I think what is the real bottleneck is how many brain cycles can you run. If you're going to be replaying, for example, from memory, well, you can't replay everything at n squared times. You have to choose the right things. So I think continual learning is the right setup, but I'm not satisfied with the way that people have been pursuing it.
So it's certainly up to maybe PhD students to find some new paths or more formalizations in that area. We're close to time, so I want to close with just one quick question. If you could recommend some unexplored areas of reinforcement learning to recommend to new PhD students, which ones would you recommend they focus on?
So obviously latent state discovery is very exciting. I think it's important. I would also say that memory is very interesting. I like the model of a situation where you have a model, you have a memory of n things, but your access time is only log n. And now I think that if it's order n access time, that's going to just kill you in terms of any kind of scale. But once it's log n, you effectively have the size of the RAM in your computer to use, and that can be the ability to kind of pull up experiences from a very large pool. I think is potentially quite revolutionary in terms of being able to solve new problems.
Anything to add, Yoshua?
Well, I'm gonna cheat a little bit here. So in addition to what John talked about, and in addition to all the things I talked about earlier in terms of subjects that touch to RL, I would add one that I would have liked to talk about, and I think is in the long run one of the most important problems for AI. And that is knowledge acquisition, like active knowledge acquisition. So exploration, but like the thing is, the state of the art right now is so stupid. Greedy epsilon something is so stupid that we ought to be able to do a lot better. And we know, babies are really good at that. We have a lot of information about how to do it. We have a lot of insights that can come from math, information theory. There's a lot of potential, and not enough people working on this.
Fantastic. Thank you so much. With that, we're exactly at time at the end of our debate. I want to thank our audience for joining us today and for the great questions that you put forward. And of course, our speakers, Yoshua and John, thank you so much for sharing your thoughts with us today.
Thanks a lot.
Thank you, Katja. Thanks, everyone.
With that, I'm going to hand over to Akshay for the closing remarks. Thank you so much.
Hi, everyone. We almost had an issue because my Teams was frozen, but so that concludes part one of today. And we're going to take a quick break for about 30 minutes and reconvene at 12:15 p.m. Eastern time in the Teams app. for the poster session. So looking forward to seeing everyone over there, and looking forward to all the really exciting posters. See you in about 30 minutes.